This is example number 3. A single acting reciprocating pump has the following data. We have stroke, piston diameter, suction pipe length, suction pipe diameter, suction head, atmospheric pressure, safe minimum pressure head as 2 meter ABS. And the question is, what is the maximum speed at which it can be run without causing separation during suction stroke? Okay, so what is separation? So separation is actually if you pull the piston very fast, maybe water do not cope. Water cannot enter the piston at the same time or at the same speed you pull the piston. So it will create a bubble. It will create an empty space in the piston. So that the idea is very simple. For example, if you use your pichagari, you shrink. So if you pull the shrink, sometimes the water bubble, or you could see a bubble there. So the bubble means actually the empty space. So the idea is simple because you pull the shrink very fast. So the liquid cannot cope, cannot follow the velocity. So this is the idea of separation. So separation means that we have a separate space between the liquid and the gas. So and then in this question we need to calculate. So what is the maximum speed? Okay, because if it's exceed the maximum speed, maybe separation can occur. So and then so we calculate the pressure head here. So the pressure head, as we discussed previously, so it can be calculated as HATM minus suction head and also minus the acceleration head. And then the acceleration head can be calculated by using this equation. So and then at the beginning, why we only calculated at the beginning? Because that is the most critical time. So if you have a jump start, means if you pull the piston very fast at the beginning, so it will create separation. Okay, so but if the flow is comes into the chamber, so if you increase the speed, so it is not easy to have the separation inside a liquid. So at the beginning, we know that the angle is 0. That will give us cos theta equal to 1. So we will have this equation. So because the cos is equal to 1 now, we substitute all the value and then, okay, we substitute all the value, but we cannot substitute the value of n because n is the value of RPM. So mean RPM is the speed of the piston actually. So we just leave the value of RPM as n, and finally we could simplify the acceleration head as 0.00233 Newton square. I'm sorry, n square. So and then we substitute into this equation the pressure head, and then from the equation we know that the safety pressure head is limited to 2. So and then we substitute the value of pressure head as 2, and then we could finally calculate the value of n, which is 47.38 RPM. So and then normally if we deal with RPM, we will round up to the nearest integer. So means that 47.38 we need to round up as 48 RPM. We go for example 4 here. A single cylinder double acting reciprocating pump has a piston diameter of 300 mm and stroke length 400 mm. When the pump runs at 45 RPM, it is discharged 0.039 meter cube per second under a total head of 15 meters. What will be the volumetric efficiency work done per second, and power required if the mechanical efficiency of the pump is 75%. So we have all the data here. So the idea, so the first question is about the volumetric efficiency. So we know that the volumetric efficiency is the flow rate for actual divided by flow rate in theory. And then because we have a double acting reciprocating here, we could calculate the theoretical flow rate as this one. We need to multiply with 2 here because you know double acting means at one time there are two action. Okay, so that's why we need to multiply with 2, and then we could get the theoretical flow rate for double acting reciprocating pump as 0.042417 meter cube per second. And then so we found that the flow rate at the outlet here is 0.039. So and then we could calculate the volumetric efficiency as this one, 91.94%. And then we could calculate the power. So power is rho GQH. So we substitute with the actual flow rate here. So and then according to the question here, so it is the total head of 15 meters. So means this pump can deliver water until 15 meters above the suction area or the input surface. So and then we substitute the value of 15. So we get it is 5.739 kilowatt. And then from the question, we need to calculate the power required if the mechanical efficiency is 75%. So we can do the calculation like this one, and then we found that the power required is 7.652 kilowatt. So this is example number 5. Following details of a single acting, single cylinder and reciprocating pumps are given as below. So we have all these parameter. So you could understand LP is the length for the piston, length for the suction pipe, and length for the delivery pipe. So and then this is the diameter for the piston, okay, diameter for the suction pipe, and diameter for the delivery pipe, and this is the atmospheric pressure, atmospheric pressure head. So this is the suction head, and this is the delivery head. So and then the value of F 0.02 for both suction and delivery pipe. So the F here is actually the friction factor for the pipes. So please do your revision. Please make revision for minor and major laws that you learn in Fluid Mechanics 1. So we will get the value of F from the Moody chart, if you still remember that. So the value of F in this problem is given straight away as 0.02. And then the idea is the safe minimum head is 2.4. So okay, this idea is actually similar with the previous question. So neglect the slip and calculate maximum permissible speed. So we need to calculate the maximum speed before the separation can occur. And number 2, energy required to drive the pump if an air vessel is provided on the delivery side very close to the cylinder. So in this situation, we need to calculate situation with air vessel. Okay, so for the total head, so we need to calculate we must make sure that it will not exceeding the safety head here. So the total pressure head as actually here is the atmospheric pressure minus suction head and minus the acceleration head. And then at the beginning, so the cos theta is actually equal to 1. So we could get this equation. So and then we substitute all the value. We could get the acceleration head at the beginning as 0.0021 at 4 n square. So and then it is given in the question that the safety head is actually 2.4. So we substitute into this equation, so we could find the value of n as 46.88 rpm. So let's say we round up the value as 47 rpm. And then we could calculate the power. The equation for the power is rho GQH, and then we could calculate the value of H by having all of these value. So we have suction head, we have delivery head, and then we have friction in suction and also friction in delivery. So friction in suction, because okay, the straightforward, the very easy one is the suction head and the delivery head. So according to the question here, we have the delivery head means the height is suction is 3, the delivery head is 10. Means that we already know the value of this one and also this one, but we need to determine what is the value of the friction head at the suction and the delivery. So first we need to calculate the suction friction head. So the equation is this one. It is okay for us just to calculate the average value. So we substitute everything, so we could get it is equal to 1.25 meter. So and then we found that the air vessel is located very near to the piston at the delivery side. So what happened to this one? So first, please remember that the air vessel can create a steady flow after the air vessel. So means that first we need to calculate what is the flow rate in the pipe. So the flow rate or the continuity equation can be calculated by using this equation. So we substitute all the value, we could get that the flow rate here is 0.004795 meter cube per second. So and then because the velocity after the air vessel is steady, so mean we need to calculate this situation using the idea of flow in pipe that we learned in fluid mechanics 1. So we start with the calculation of the velocity inside that pipe, because we know the flow rate is 0.004795. We divide with the cross-sectional area for the delivery pipe. So we found that the velocity inside the delivery pipe is 0.61 meter per second. So and then we could calculate the losses in delivery pipe. So losses in delivery pipe need to be calculated similar to what you learned in fluid mechanics 1 about the major losses in pipe. So we have L, we have F, L over D, V square over 2G. So we substitute everything. So the U here is the velocity at the delivery pipe. So and then it is equal to 0.0569. So here you could see that the length of this delivery pipe is 15 meter, but it is only give us a friction of 0.05. And then if we compare with the friction at the suction pipe, so suction pipe is still fluctuated, means there are no air vessel in suction pipe. So we found that the friction of the suction pipe, the length of suction pipe is actually 3 meters. Okay, the length of the suction pipe here is actually 5 meters here. So it is 1/3 compared to the delivery pipe. but the value of the friction here is very large compared to the friction for the delivery pipes. That's why the advantage of the air vessel is actually could reduce the friction or resistance inside the pipe. So and then if we calculate all of this, we could get that the total head is 14.3 meter. We substitute into this equation, so we could calculate that the power output of that pump is actually 673 watt.